Welcome back to topic 42 for Algebra 2, Graphing Rational Functions. In part 1, we're going to identify what is the graph of a rational function, the parent function, domain and range for the parent function, as well as asymptotes and holes in the graph. For graphing rational functions, there is a specific name related to a rational function. It's called a hyperbola. So the graph of a rational function is called a hyperbola. Now this graph is made up of symmetrical parts. It kind of looks like boomerangs, but they're called specifically branches. Now the parent function of a rational function is y equals 1 divided by x. Now, sometimes we may see this as y equals x to the negative first, but remember, we don't write our final answers with negative exponents, so we're going to move that variable of x down to the denominator and write it as 1 over x. This is also the inverse function. Now, to our right, we see the graph of this parent function. Notice how we kind of have two curves here. These are our branches. And how the graphs approach certain values but never actually touch them. So if we want to think about the domain, remember, the domain is all of our x values. So if I look on the left-hand side of my x-axis, I start at negative infinity. And since it's negative infinity, and infinity is not finite, that's why we're using parentheses. Now, as I keep going to the right, I get infinitely close to 0, but I never actually touch it. So the domain is from negative infinity to 0. Now, because I never touch it, that's why there is a parentheses here. But notice on the other side of the graph, we start back up at 0 and go to positive infinity. Therefore, there needs to be a union. And we have this union because we have an asymptote, which we will define in the next slide. Now remember, the range is all of the y values. So if I look at my y-axis, I start at negative infinity, and as I'm increasing and increasing, I'm approaching 0, but I never actually touch it. However, then on the other part of the graph, I start at 0 and then approach positive infinity. So again, here is why we're dealing with a union. And because my graph doesn't specifically include 0, that is why we have parentheses. Moving on to the next slide. So recall that rational functions is the quotient of two polynomials. Let's say p of x and q of x are polynomials, and where q of x in the denominator cannot equal 0. Now asymptotes are where the line of the graph approaches but never touches. Another name for asymptote is called a non-removable discontinuity. I totally spelled that incorrectly. Removable, oh goodness. so I'm not an ELA teacher. Discontinuity. Now we're going to see later in part 2, where we deal with actual examples with polynomials, the difference in between non-removable discontinuity as well as removable discontinuity, which we will define later in this slide. So there are two types of asymptotes. There are vertical asymptotes and there are horizontal asymptotes. Vertical asymptotes is what we were exposed to earlier in this unit. The vertical asymptote occurs when the denominator equals 0. So if we think back to the previous topics, that's what we dealt with the restrictions on the domain. So in order to write the equation for a vertical asymptote, since it's a vertical line, we're dealing with our x variable. And x is going to equal a number. So that's our equation. Now there can be more than one vertical asymptote. So let's look at this example below. 3x minus 2 over x squared plus 7x plus 12. Now since we're just focusing on the denominator with a vertical asymptote, I don't need to think about the numerator right here, at least because it's already in the most factored form, 3x minus 2. So I'm just going to look at my denominator. I can factor x squared plus 7x plus 12 to be x plus 3 times x plus 4. Setting them both equal to 0 to figure out what x cannot equal, that would make the denominator equal to 0 and ultimately undefined. So here we can use the zero product property. X can either equal -3 or -4 in order to make the denominator equal to 0. So these are our vertical asymptotes. And usually when we graph them with dashed lines. Just as an FYI. So in addition to vertical asymptotes, there are also horizontal asymptotes. Now, horizontal asymptotes are a little bit more complex. There's actually 3 cases that we need to consider with horizontal asymptotes. So if we look at our problem, and if we notice the degree of the numerator is less than the degree of the denominator, and when I say degree, I'm referring to the highest degree, the highest power. So in our example here, we have y equals x plus 4 divided by x squared plus 1. So the degree in the numerator, the highest power is 1, whereas in the denominator, it's 2. So 1 is less than 2. Our horizontal asymptote will be y equals 0. And again, since we're dealing with a horizontal line, it's y equals. But why is this? So with a graph, remember how we plug in values for x and get outputs of y. So if we keep plugging in bigger and bigger and bigger values for x's, so as x increases, this fraction will become smaller and smaller and smaller and smaller. So it's going to approach 0. It's going to get closer and closer and closer to 0. Now, with every function, sometimes we deal with transformations. So if we have a vertical shift, in this case, if we have a plus k on the outside, if we have our fraction that's becoming closer and closer and closer to 0, and then we have that vertical shift outside of that, the sum of those two values would be 0 plus k, or just k. So if we have this vertical shift, this vertical transformation, then we could have our horizontal asymptote be equivalent to whatever number k is. Now, what if the degree of the numerator is equal to the degree of the denominator? For example, what if they both have the same highest power? So in our example here, 2x squared plus x plus 1 divided by x squared minus 1. All we really need to focus on here is the highest power. So I can forget about the other terms for this moment. All I need to do is take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. So in this case, we have 2 divided by 1, which gets us 2. So my horizontal asymptote will be y equals 2. Now lastly, what if the degree of the numerator is greater than the degree of the denominator? For example, what if we have x squared plus 1 over x plus 1? So in this case, my 2 is greater than the first power. Here we have no horizontal asymptote. And you will specifically look at this scenario later in math courses, but not right now. Right now, we'll just be satisfied with there will be no horizontal asymptote. Now, remember before how I mentioned how asymptotes are non-removable discontinuity? Well, there is a thing such as removable discontinuity. That is specifically called a hole in the graph. And this occurs when you have your polynomial in the numerator and your polynomial in the denominator, and they have a common factor. So if we were to factor the numerator and factor the denominator, and if they share that common factor, what would we do? Well, most likely we would cancel it out because they would reduce to 1. So because they cancel out, this is called a hole in the graph. We are literally removing a factor from our rational function. So in order to figure out where this hole will physically appear in our graph, we're going to take our factor and set it equal to 0 in order to solve for x, just like we were doing with a vertical asymptote where we solve for x. However, a hole is going to be a point on our graph. So we need a y value for this. So we can plug our x back into the key point here, back into the reduced equation to get y. Now notice I caught myself there. 1, I made a mistake. And 2, it's important to look at the reduced equation. So once we eliminated that factor, we need to plug our x value back into our now simplified version. We'll see this in an example as to why we have to do this. Our hole in our graph will then appear at this point. We'll have an x value and a y value. So that is part 1 for topic 42 for graphing rational functions for Algebra 2. Thank you for watching.